Students, this is lecture 12 of first chapter, Fundamentals of Design, and in lecture 12, today we will discuss numericals based on various types of stresses. So here, first numerical, an MS rod of diameter 12 mm was tested under tensile test with gauge length of 600 mm. Following observations were noted. Final length is 800 mm. Final diameter is 8 mm. Yield load is 4 kilonewton and ultimate is 6 kilonewton. Calculate yield stress, ultimate stress, percentage reduction in area and elongation. Whenever we start any numerical, first of all in the solution we must write given data. So here we are given initial diameter 12 mm, final diameter 8 mm, initial length is 600 mm, final length is 800 mm, yield load is 4 kilonewton, so 4000 Newton, ultimate load is 6 kilonewton, so it is 6000 Newton. We will first calculate initial area by using formula pi by 4 di square, which comes 113.09 mm square. Then we will also calculate final area by using formula pi by 4 df square, which is equal to pi by 4 into 8 square, which comes 50.265. First we have to calculate yield stress. So to calculate yield stress, we will use formula yield stress is equal to yield load upon original cross-sectional area. So we will substitute values here, yield load and original area, which comes 35.37 Newton per mm square. Similar to this, to find the ultimate stress, we will use formula ultimate load upon original cross-sectional area. After substituting values of original load and ultimate load and original cross-sectional area, we will get ultimate stress equal to 53.05 Newton per mm square. Now we have to find percentage reduction in area. So if I want to find only difference in area, then difference in area will be AI minus AF. But percentage reduction in area will be AI minus AF, the whole divided by AI, and it will be multiplied by 100. So we can see here, this is the formula, AI minus AF upon AI into 100. After substituting values, we will get that when a material diameter will change from 12 to 8, there is a 55.55% reduction in area. Then we will see increase in length, that is percentage elongation. So here for percentage elongation, friends, we will use formula final length minus original length upon original length. So it comes 33.33% elongation, though length is increased from 600 to 800 mm. Increment in elongation is 33.33%. Now we will see next question. In this question, we are given a press which exerts a load of 2 meganewton. This load is carried by the two rods. Length of the rod is 2 meters and that supports the upper head of press. We have to find diameter of rod and change in the length of the rod. Assume safe stress as 80 megapascal and modulus of elasticity is 210 kilonewton per mm square. So we will first write given data. Given load on the press is 2 meganewton, which comes 2 into 10 raised to 6 Newton. Length of rod is 2000 mm, so there are two such rods. Tensile stress is 80 megapascal and modulus of elasticity is 210 into 10 raised to 3 Newton per mm square. So students, here you can see that this is the press head and these are two rods. So when press head will fall down, load will come on these two rods. We are going to find out the diameter of the rod. So first to find the diameter of the rod, because total load is shared by two rods. So first we will calculate the load which is carried by each rod. So it will be equal to P1 upon 2. So it comes 1 mega Newton or 1 into 10 raised to 6 Newton. After we calculate load on each rod, we will now find out the diameter of rod. And students, you have seen that rod is subjected to tensile failure when head will fall down. So considering tensile failure of each rod, we will use formula tensile stress is equal to force upon area or load upon area. As rod is circular, formula of area is pi by 4 d square. After substituting values and rearranging the terms, we will get diameter as 126.15 millimeter. So for this is just a safe value. So for making our design more safe, we will increase our value and say diameter can be 128 mm. Now they have asked us to find the change in length of the rod. We have seen the formula of change in the length of the rod. Delta L is equal to PL upon AE, that we have used. So PL upon AE, in that P upon A is stress. So we can use this formula as sigma T into L upon E. We will substitute all values and we will find change in length of the rod, which comes 0.74 mm. Next question is for cast iron link, which is subjected to a tensile load of 45 kilonewton, and we need to find the stresses induced in that link material at section AA and section BB. Here we can see that load which is acting on the link is 45 kilonewton. Here we will find the stress in the material at section AA. It is cut section. So when we will see area of section AA, it will be 45 into 20. When we see cut section of BB, it will be a hollow rectangle with width 20 and depth is a difference of 75 and 40. So one by one we will see at section AA, tensile stress is equal to load upon cross sectional area at AA, and the answer is 50 Newton per mm square. At section BB, tensile stress is equal to load upon area at BB, which is 75 minus 40 into 20. So stress induced in the section BB is 64.25 Newton per mm square. Next, another simple question is for a reciprocating steam engine, and the diameter of the piston is 300 mm. Steam pressure is 0.7 Newton per mm square. If compressive stress is 40 megapascal, we need to find the diameter of the piston rod. So we will first write given data, diameter of piston rod we have to find, and piston diameter is 300 mm. We will denote it by capital D. Steam pressure, we'll write small p, 0.7 Newton per mm square, and sigma T is 40 Newton per mm square. First of all, there is a cylinder, and inside the cylinder there is a piston, and below here there is a steam. So steam will exert a pressure and it will apply the force on the piston. So how much the force is exerted on the piston? That will be equal to steam pressure into area of the cylinder. So we will find out the load acting on the piston is equal to area of the piston into the pressure. That pressure is a steam pressure. So we have got the value of the load by substituting all the values. Now to find the piston rod diameter. So you can see that piston rod is here. This is the piston rod and here there is a piston. So when force is exerted by the steam when piston will move from BDC to TDC, piston rod will be subjected to compression. When again it will come down, we can say that rod will be subjected to tension. So rod will be subjected to tension or compression. So if we consider a compressive failure, because we are given a compressive stress, then the formula of compressive failure of piston rod is sigma C is equal to load upon area. Here we will denote the diameter of piston rod by small d. So after substituting all the values here, sigma C value, P value and pi by 4 is a constant. After rearranging the terms, we will find diameter of piston rod, which is minimum required as 39.68. So we will take its next higher value. You can take 42 mm, you can take 40 mm, both will be right. Next sum is very simple. Find the maximum diameter of the hole that can be punched in an MS plate of 10 mm thickness. Ultimate shear stress is 220 Newton per mm square and crushing stress is 350 Newton per mm square. So we will write given data. T is 10 mm. Ultimate shear stress is 220 Newton per mm square and crushing stress is 350 Newton per mm square. First of all, whenever there is a plate and the punch will fall on the plate, the force required to punch a hole, because hole will fall down like this way, it will fall down like this way. So there is a circumferential shearing. You can see here contact is circumferential. So formula is force required to punch a hole is equal to pi into d into t, where d is the diameter of hole, t is the thickness of plate, that is the area, circumferential shearing area, into ultimate shear stress. We will be using this formula and substitute the values. As we do not know d, our force required will be in form of d. D will remain unknown and it comes like this way. Now punch is falling on the plate. So which force will act on the punch? There will be a compressive force on the punch. Punch material is circular. So when we take a compressive force over here, what will be the area of failure of a punch? Area of failure of a punch is a circular area. Circular means diameter of punch. So it is pi by 4 d square. So when we talk about the crushing failure of punch, W is the cross-sectional area of punch into crushing stress. So we'll write this formula. We will substitute values of sigma ck and pi is constant. So we get the crushing load on the punch is equal to something d square. Whatever force is required to punch a hole, that force only is exerted by a punch. Both W should be same. So we will compare equations 1 and 2. After comparing equation 1 and 2, 1d will be cancelled out and d will be equal to 6911.5 upon 274.889, which comes 25.143. So we will write, say d is equal to 26 mm. Next question is of knuckle joint. So here we can see that circular rods there are two rods which are to be connected, and we are going to connect that rods by means of knuckle joint. This is a knuckle joint. There is a pin which is inserted between forked end and single eye. We are going to apply a pull over here which is of 120 kilonewton. Diameter of rod is 50 mm and diameter of pin is 40 mm. We need to find out the tensile stress which is induced in the rod and shear stress in the pin material. Let us write given data. We'll denote diameter of rod as capital D and will denote diameter of knuckle pin as small d, and W is 120 kilonewton. So friends, as we can see that load is acting here. So when load is acting here, rod is here. So rod is subjected to which failure? Tensile failure. So considering tensile failure of the rod, sigma T is equal to W upon area of rod, which comes pi by 4 into capital D square. Knowing all the values after substitution, we will find out this tensile stress induced in the rod material. Now students, you can see here that pin is inserted between fork end and single eye. Pin is inserted. When single eye will move this side, forked end will move this side. Pin will be divided into 3 pieces, and that failure of the pin is a double shear failure. So here friends, you can see this is one area of failure which I have shown by curling lines, and this is another area of failure. So as it is double shear, equation of area will be 2 pi by 4 d square. So tau induced is equal to W upon 2 pi by 4 d square. Substituting all the values available with us, we have found tau is equal to 47.74 Newton per mm square. Next question which we will discuss today, that is also of the knuckle joint. Here the knuckle joint is required to transmit a load of 80 kilonewton between the bar X and bar Y. Here we are given the permissible stress values of the rod material, that is 100 Newton per mm square, and permissible shear stress for pin material is 80 Newton per mm square. And here we are supposed to find diameter of bar, or you can say rod, and diameter of pin. So you know that rod is subjected to tensile failure. Previous sum only we have discussed this. And pin will be subjected to which failure? Double shear failure. Same principle of previous sum we will use. Considering tensile failure of each bar or rod, sigma T is equal to P upon area. Rod diameter will denote it by capital D. So after substituting values and rearranging the term, we will find diameter of the rod which is 31.91. So we will assume it equal to 32 mm. Let us assume small d is the diameter of knuckle pin, and as knuckle pin is subjected to double shear failure, so formula used will be tau is equal to W upon 2 into pi by 4 small d square. Substituting values, we can find diameter of knuckle pin as 25.23 millimeters. So we can say 26 mm. So students, I hope you have enjoyed all lectures. This is 12th lecture of chapter 1, and I have given my best to explain you all the topics. Thank you very much.